This week we will study RC circuits. These are circuits whose elements are resistors and capacitors. The object of this lab is to measure the potential difference across capacitor as a function of time, when it is charging and discharging, and use this information to determine the capacitance of a given capacitor. A capacitor gets its name from the fact that it has capacity to store both electric charge and energy. Capacitor is nothing more than two conductors, usually called plates, separated by a finite distance. When these plates are connected to the terminals of a battery, they become charged. One plate acquires a charge positive Q and another plate equal and opposite charge negative Q. The charge Q is proportional to the applied voltage, and constant of proportionality is defined by the capacitance of the capacitor. C is equal Q over V. As we can see from this relation, the units of capacitance are coulombs per volt. In the standard system, this combination is referred to as farad. The capacitance of capacitor depends on its physical characteristics. For example, a capacitance of a sphere of radius r is given by C is equal 4p epsilon 0 times r, while for a parallel plate capacitor, capacitance is given by this equation, C is equal epsilon 0 a divided by d, where a is the area of each plate, d is the separation distance between the plates, and epsilon 0 is equal to 8.85 times 10 to negative 12 coulomb square per Newton meter square is a permittivity of free space. A common form of energy storage device is a parallel plate capacitor. When a capacitor and resistor are connected in a circuit, we can either charge or discharge it depending on if it is already discharged or charged. Let's now take a look at a simple RC circuit. Initially, the switch is open and there is no current in the R or charge on the capacitor. At the time t equals 0, switch is closed and current begins to flow. If the resistor is not connected in a circuit, the capacitor will immediately take on the charge Q is equal C times epsilon, where epsilon is a potential on the battery. The resistor is used to slow the charging process. The larger the resistance, the longer it takes for capacitor to charge. This is because there is a potential drop across resistor, so the potential difference across the capacitor is less than EMF on the battery. With less voltage across the capacitor, there will be a less charge on its plates compared to that of the capacitor were connected directly to a battery. The charge on capacitor changes with time according to this equation. Q of t is equal C epsilon 1 minus e to the negative t divided by RC, where RC is tau and is referred to as a time constant on the circuit. The quantity tau is equal RC is in fact time. This means that ohm times farad will give units of time. Now let's check this. We know that ohm is defined as a volt divided by ampere and farad is a coulomb divided by volt. From the definition of current, we know that ampere is defined as a coulomb divided by seconds. Now the volts here will cross out as well as coulombs and we are left with units of seconds. For time equals 0, the e to the negative 0 divided by RC will be equal to 1, and then from the equation for the charge on a capacitor we get that at time equals 0 the charge on the capacitor is equal to 0. As the time increases, essentially goes to infinity, the e to the negative infinity over RC is going to be equal to 0, and then from the equation for the charge on the capacitor we get that at a very long time the charge on capacitor will be equal to the capacitance of the capacitor times the epsilon, which is the EMF on the battery. At time equal tau, the charge of capacitor will be 63.2% of its initial charge. From this figure, we see that initially capacitor charges rapidly, indicating a large current in the circuit. After some time, the charging slows down because the larger the charge on the capacitor, the harder it is to transfer additional charge against the electrical repulsive force. Later, the charge barely changes with time, which means that current is equal to zero. The current in RC circuit changes with time according to this equation. I is equal epsilon divided by R e to the negative t divided by RC. Initially, at time t equals 0, e to the negative 0 divided by RC is equal to 1, so the current at time equals 0 will be equal to the epsilon divided by R, which is a potential across the battery divided by the resistance of the resistor. This is same as if the capacitor is not present in the circuit. As the time goes to infinity, e to the negative infinity over RC is equal 0, so then the current at a really long time becomes 0. So this graph here gives you how current behaves while charging the capacitor in RC circuit. As the time increases, the current goes to 0. The capacitor is fully charged, so no more charge can flow onto its plates. The equation that will show how potential changes over time when capacitor is charging is Vc is equal epsilon 1 minus e to the negative t over Rc. So initially, at the time equals 0, the potential across the capacitor is going to be equal to 0, and then as the time increases to infinity, the potential across the capacitor will be equal to the potential across the battery. Now we will talk about the process of discharging capacitor through a resistor. The initial charge on the capacitor is Q. Initially, the switch is open and no current can flow. When the switch is closed, current flows from the positive plate on the capacitor to the negative plate, and the charge on capacitor changes with time. The charge remaining on the capacitor will approach 0 after several time units, and these time units are RC. For the discharging capacitor, charge on the capacitor changes with time according to this equation. Q is equal Q e to the negative t over RC. The current changes according to this equation. I is equal negative epsilon over R e to the negative t over RC. And the potential difference across the capacitor during discharging process will change with time as Vc is equal to the epsilon e to the negative t over Rc, where R is the resistance of the resistor and then epsilon is the potential across the battery. Let's first see how the charge behaves for the discharging capacitor over a period of time. At initial time t equals 0, the charge on the capacitor will be equal to Q. As the time increases, the charge on capacitor will go down to 0. The capacitor will fully discharge. Potential will behave the same way. From this graph you see at the time equals 0, the potential across the capacitor will be at Vc, which is going to be equal to the potential across the battery. And then as the time increases, the capacitor will fully discharge, so the potential across the plates of the capacitor will go down to 0. The current will behave this way. So at the time equals 0, the current will be equal to the negative epsilon over R. And the reason for this is because the current is flowing from the positive capacitor plate to the negative capacitor plate. And after a really long time, the current on the circuit will go down to 0. As we already stated earlier, during this experiment we will measure potential difference across the capacitor as a function of time for charging and discharging process. Furthermore, we will use this information to determine the capacitance of the capacitor. Now, knowing the equations for the potential across the capacitor's plates for the charging and discharging process, we can linearize this equation and then solve for the time. From here, we can plot these two equations and determine the capacitance of the capacitor. So for the first equation for the charging process, we can simply rearrange the terms, and then since we have this term e to the negative t over rc, we are going to take a natural log from the both sides of the equation, and then we are going to end up with ln 1 minus vc over epsilon is going to be equal to the negative t over rc. Now, if you plot a straight line of this term here, ln 1 minus vc of the epsilon, as a function of time, from the slope of this straight line, knowing the resistance of the resistor in our circuit, we can determine the capacitance of the capacitor. Similarly, for the discharging process, we are starting from the equation for the potential across the capacitor for discharging. Now, rearranging terms, we get this term here, and then by taking a natural log from the both sides of the equation, we end up with ln vc over epsilon is equal to the negative t over rc. Same as before, if you plot ln vc over epsilon as a function of time, from the slope of this curve we can determine the capacitance of the circuit knowing the resistance of the resistor. For our experiment, epsilon is going to be V0, and that number is set to 4 volts, and the resistance of the resistor will be given. Now I will show you how to collect data for charging and discharging capacitor through two different resistors. This is a setup for this week's experiment. Here we have a charge-discharge circuit board that contains a 1 farad capacitor. It has 3 resistors, 10 ohm, 33 ohm and 100 ohm resistor. It has 3 3-volt light bulbs, and then has this switch here that is used to either charge or discharge the capacitor. So first I'm going to show you a data collection, and then after that I will explain the data analysis. The circuit is already connected, so there is no need for you to disconnect or connect the circuit again. Towards the middle of the experiment, you will just have to move one wire and then return it back to its original position. The circuit looks like this. So from the slave side of the power supply, you're connecting to a positive and negative terminal of the circuit board. Then from this middle side, from the switch, you're connecting to a positive side of the capacitor, and then from the negative side of the capacitor you're connected back to a 10 ohm resistor, and then from the 10 ohm resistor we don't have to use any cable, but here on the circuit board you can see that we are closing the circuit to a negative terminus of the board. And then lastly, here is a voltage probe that is connected to channel A of the science workshop, and through this voltage probe we will collect the change in potential across the capacitor as a function of time, and then use that data to determine the capacitance of this capacitor. So at the beginning of the experiment, the switch should be at the discharge position. So once you're ready to start collecting the data, you're going to log into the student account, and then either from the folder 1102 if you're registered for 1102 class, or from the folder 1122 if you're taking 1122 class, you're going to open the experiment on the RC circuits. Once the Data Studio opens, Data Studio is already programmed to collect the data for 200 seconds. So the power supply is already preset to a 4 volts, and you shouldn't change this. So you're going to press the start on the Data Studio and then wait for a couple of seconds, 5 or 10, and then you're going to slowly move this switch to a charge and now you're going to wait for 200 seconds for the capacitor to fully discharge. As I said, the Data Studio is programmed to stop the data collection after 200 seconds. If, when you are at a discharge position, if the potential on the Data Studio doesn't show initially 0, that means that the capacitor was not properly discharged from the previous class. Return this switch to a discharge position and wait until the potential is shown to be 0. After that, you can start collecting the data following the steps. So press start, wait 5 to 10 seconds, and then move this switch to a charge, and now you're going to wait for 200 seconds for the capacitor to fully charge. Once 200 seconds is up, you're going to start collecting the data for discharging the capacitor. So now you're going to press start again, wait for a couple of seconds. Potential now should be at the maximum, around 4 volts, and then after 5 to 10 seconds you're going to move this switch to discharge and wait for 200 seconds up until the data collection on Data Studio stops, and then you're done collecting the data for discharging the capacitor. Once you're done collecting the data for charging and discharging capacitor through a 10 ohm resistor, now you're going to take this cable here, the one from the 10 ohm resistor, and move it to a 33 ohm resistor. So now we are going to repeat the same thing again, but this time we are charging and discharging capacitor through this 33 ohm resistor. Now you're going to repeat the same steps. You're on the discharge, press start for the data collection, and then wait 5 to 10 seconds, and then move the switch to a charge. Wait up until the data collection is stopped by the Data Studio. That's 200 seconds. Once you're done, then you're going to press start again, and then again wait 5 to 10 seconds, so the voltage now should be at the maximum, and then turn this to a discharge position and wait up until 200 seconds is up. So now you're going to have 4 runs for the potential as a function of time on your computer. Okay? Once you're done, return this cable here to a 10 ohm resistor and leave the switch on the discharge position. So next I'm going to show you how to do a data analysis on the data that you just collected. Now when we are done recording the data for the charging and discharging capacitor through a 10 ohm resistor, and also for charging and discharging capacitor through a 33 ohm resistor, we can move on to a data analysis. It is important here to mention that this red curve represents a charging of the capacitor through a 10 ohm resistor. That is run number 1. Green curve here represents a discharging of the capacitor through a 10 ohm resistor. This is run number 2. The blue curve is a charging of the capacitor through a 33 ohm resistor. This is run number 3, and the orange curve or run number 4 is a discharging of the capacitor through a 33 ohm data resistor. The data is collected for 200 seconds as the Data Studio is programmed to stop data collection after 200 seconds. So these curves here represent a voltage as a function of time. Since the equations that explain how the voltage across the plates of the capacitor change for the charging and discharging capacitor have the e to the negative t over RC term, to linearize these equations we had to take a natural log of the both sides. If you remember from the lecture notes, we got that natural log of 1 minus Vc over epsilon, or in our case V0, is going to be equal to the negative t over RC for the case where the capacitor is charging, and then for the case when the capacitor is discharging, the ln of Vc divided by epsilon, or in our case V0, is going to be equal to the negative T over RC. Now if you plot the left-hand sides of the equation as a function of time, from the slope of that curve we can calculate the capacitance of the capacitor knowing the resistance of the resistor. So first, to analyze the data for charging the capacitor through a 10 ohm resistor, we need to add the equation for the linearization of this curve. So we're going to click on calculate and then click on the new to define the variable. So now we are going to call this variable LVC. Type LVC equal to ln, open parenthesis, 1 minus, and then we are calling the voltage across the capacitor VC10. So this is our variable VC10, divided by V0. V0 is a constant, and that is the value of the potential that we set on the power supply, and that was 4.0 volts. Now close the parenthesis, click on accept. Now here it says please define variable VC10. So run number 1 was the run when we charged the capacitor through a 10 ohm resistor. So we are going to click on run number 1, drag and drop it here, and then click on yes. Now our variable is defined. Click on the properties, under variable name, erase y and type LVC, and then for units we are going to have volts. Now click OK and then click on accept. Now we can go ahead and graph this LVC versus time. So simply drag and drop on the new graph. And now we are getting, so this is the part before you switch to charging, and this is the part where we're charging. So this is LVC versus time, where LVC represents ln 1 minus Vc over V0. These curves here on the end of the graph, they represent a potential dependence for the charging of the capacitor. So simply you're going to highlight the portion of the line that is straight, and then click on the fit and choose the linear fit, and you're going to get a slope. Now this, from the equation, you're going to determine what does this slope represents and use this slope to calculate the capacitance of the capacitor, knowing that the resistor used in the circuit has the resistance of 10 ohms. Once you're done with this, you're going to name this graph simply by clicking here once and another time, and then so this is charging. So label it as a charging 10 ohms, and then write your name and your partner's name and print one copy of the graph for each member of your group. If this graph represents the charging of the capacitor, it is important to label it as a charging and which resistance you used, since you're going to have a quiz over this experiment in 2 weeks, and it will help you to better prepare. Now, once you're done with calculating the capacitance for the charging of the capacitor through a 10 ohm resistor, we are going to calculate the capacitance again now for the discharging the capacitor through a 10 ohm resistor. So again, click on calculate and now click on new, and now we are going to define LVD. So this is LVD here represents a ln is equal to ln, open parenthesis, again VC 10 divided by V0, and V0 is 4.0 ohms. Click on accept, and now here it says please define variable VC10. So we are analyzing the discharging of the capacitor through a 10 ohm resistor. So that was our run number 2. Take run number 2, drag and drop here, and now click on yes, and your variable is defined. Now click on the properties. Under variable name area is Y, and type LVD, and then for the units use volts. Click on accept and close this. So now again we are going to plot this graph to a new graph, and then enlarge this. So you see that for the discharging there is a huge potential dependence. Again, select the portion of the graph that represents a straight line, and highlight it, and then click on the linear fit. Click on the fit and choose linear fit, and now again you have the slope. From your equation, determine what does the slope represent, and then calculate the capacitance of the capacitor, knowing that the resistance of the resistor is 10 ohms. Next step is again to name your graph. So this is discharging. Through a 10 ohms, and then write your name and your partner name, and then print for each member of your group one copy of the graph. Now follow the steps in your laboratory manual to complete the further calculations. Now to analyze the curves for the charging and discharging the capacitor through a 33 ohm resistor is much easier because you have already defined LVC and LVD. To calculate the capacitance for the charging the capacitor through a 33 ohm resistor, double click on LVC, and now take run number 3, because run number 3 is for the charging. Drag and drop it here where it says the variables. Click on yes. Once you're done, click on accept and close this, and then similarly double click on LVD, and now take run number 4, because run number 4 is for discharging. Drag and drop under variables, and then click yes, and then click on accept, and then close this. So now your graph that states charging through a 10 ohms, you just need to change here 10 to 33, and then to get the slope, again highlight the portion of the graph that is a straight line, and you have the slope, and then from the equation, again knowing what the slope represents, you can calculate the capacitance for the charging of the capacitor, knowing that the resistance is 33 ohms. Print a graph for you and for your lab partners. And now go to the discharging graph. So you have to change here 10 ohms to 833 ohms. And then again highlight the portion of the graph that represents a straight line, and then record the value for the slope to your laboratory manual, and then knowing from the equation what does the slope represent, you can use this value to calculate the capacitance for the capacitor discharging through a 33 ohm resistor. Again, print this graph for you and for your lab partner. On the end of this experiment, you should have 4 graphs. 2 graphs for charging the capacitor, one through 10 ohm resistor and one through 33 ohm resistor, and 2 graphs for discharging the capacitor, one through 33 ohm resistor and one through 10 ohm resistor. Now follow the instructions in your laboratory manual to finish the data analysis and answer the questions. Once you're done, please close the Data Studio, do not save anything, and log out of the student account, and make sure that you leave the station in exactly same condition you found it when you walked into the lab. This is all for this week. Thank you.